Hi everyone, third video for week 5. So we talked about exponential functions, the graphs, looked at some examples, some applications, disease modeling and compound interest where they occur naturally. Today we're going to talk about logarithmic function. So the simple definition is that they are inverses of exponential function. Just as we learned trig functions and then their inverses, for exponentials the inverses are called logarithms. So let's see even before we look at properties of the function or how to work with it, let's see what we expect of the function. Because we kind of know what inverse functions do. So let's see. Exponential function 2 to the x, when the input is 1, the output is 2 to the 1, which is 2. When the input is 2, the output is 4. When the input is 3, the output is 8. When the input is 4, the output is 16. Now if this is an inverse function, it's a mystery function, we can still guess, because remember, an inverse function takes the output of the actual function as input and gives the input of the original function as output. So if I replace these four numbers here, 2, 4, 8, 16, then this inverse for 2 gives me 1, which is the input here. For 4 gives me 2, for 8 gives me 3, for 16 gives me 4. And now we gotta see how to write this function. So this 2, this information is fixed, so it's essential. We use log and we store this information 2 as a subscript. So this is still called base. Remember, in exponential function 2, this number is called a base, x. So that's how we're going to write this function. So basically what this is saying is log 2 is 1, log 4 is 2, log 8 is 3, log 16 is 4. So what this is doing, this function, it really is counting the exponents. So for example, here it's saying, if I want 2 to become 8, what should my exponent on 2 be? It should be 3. If I want 2 to be 16, what should my exponent on 2 be? It should be 4. Formal definition, y equals log a x, where a is the base, and again same conditions, positive but not 1. Now we have some properties which kind of follow naturally from the exponential property. Log of 1 is always 0 because a to the power 0 is always 1. Similarly, log of the same base of the same number is 1, and that's because a to the power 1 is a. An extension of this, log base a to the x is x, because you can just move this a over to get equality. This is because for inverse functions, we say f of f inverse is equal to f inverse of f equals identity, right? Or gives you back x. They cancel each other out. Because here, this is a function exponential of a, and then you're applying log of a, so you get back x. And the same reason for this one here, you're applying log and then exponential, so you get back x. Now in general, if you have this exponent m, then this exponent n, it can be moved in the front, so it becomes n times, and it can be seen directly from a multiplication formula. Multiplication becomes addition and division becomes subtraction. In exponential, you have exponents adding up, so that's kind of the reason, because the exponents add up, and because log functions are counting exponents, they get added and they get subtracted when you divide them. So those are the basic properties. Let's look at the graph. Again, we're going to look at two ways here. first is, let's just draw a chart. X, Y. Now in this case, we need X to be positive. Yeah. Why? Because remember that the domain of the inverse function equals the range of the actual function. Now the range of exponential function is 0 to infinity. It's always positive. Yeah. Exponential functions are always positive. It can never give you a negative result. And so the domain of this function log is always positive. So we don't even plug in 0. But we know that when I plug in 1, I get 0. When I plug in 2, I get 1. When I plug in 4, I get 2. Plug in 8, I get 3. What happens if I plug in 2 to the negative 1? Let's see. Log 2, 2 to the negative 1 jumps in front, negative 1, log 2, 2, which is 1. So it becomes negative 1. Another way is count the exponent. How do I go from 2 to the negative 1? The exponents I need are negative 1, meaning I have to fraction them out. Negative 2 gives me negative 2. So my domain is x greater than 0, so I don't have to worry about this half. And I know when x is 1, right here, 1 comma 0. And then it increases, right? As x increases, y increases, but slowly. And as x decreases, y decreases, but fast. Because when you go from half to 1/4, it was gone like double lower, right? Negative 1 to negative 2. And because it's negative, it's going to be over here. So the graph is going to look like that. Again, these are never going to meet. Now another way, remember, if you have a function and you want to plot its inverse, how do you do that? Is you take the reflection around y equals x. Okay, that's something that you do in Math 103 too. So if I reflect it along this line, this is going to go to the x-axis and become 1 comma 0. This is going to go over here, and this is going to flip over here. So that would give me the graph of log. Okay, negative log base 2x. So once you have log base 2x, which is 1, 0, then you use a transformation. Now you're making all of this negative. If you're making all of this negative, that means your output is, if it was negative before, now it's positive. And if it was positive before, now it's negative. Basically, what's that? Reflection, x-axis. So this point doesn't change, but the behavior just changes. What about log base 2 negative x? Well, I can go from here. Changing x to negative x means reflection around y-axis. So now instead of not being in the negative, it's going to not be in the positive. And this point, when you reflect it, it's going to go to negative 1, 0. This goes down. So that would be log base 2 of negative x. Now you may think, well, didn't you say log does not take negative values? Which is fine, because here if you see x is negative. So if x is negative, negative x is positive. Which is why we have the idea of domain, right? Because here the domain is going to be x less than 0. And then you have the regular transformations of x and y. So again, log base 5 doesn't really change the fact that it's going to be 1, 0 here, because log of 1 is always 0. But if you're adding 2, means you shift up by 2. So this 1, 0 now shifts up. So what is it now? It's 1, 2. So it's somewhere else that it becomes 0. Similarly here, you start with log base 10 of x. Now you change x to x minus 3, which you've seen amounts to moving it to the right by 3. So this becomes 4, 0, and it never reaches 3. I'm going to stop this video here and then continue in the next video.